Well, good morning. We are going to start off with doing three-dimensional surfaces. Last day we talked about cylindrical surfaces. Today we're going to talk about three-dimensional surfaces. Now I want you to think back to Calc 1 for a moment. In Calc 1, you generally graphed functions and you did derivatives, you found out where the critical values were, points of inflection, all that kind of stuff. And the reason it wasn't so that you could get good at graphing. I mean, you have a graphing calculator. The reason was so when you looked at a function, you knew what it was supposed to look like. So if you were going to find the area bounded by two functions, let's say, you had to know what the functions look like so you could determine your boundaries. Well, we're going to do the same thing in 3D. I want to be able to look at surfaces that potentially intersect, maybe enclose something. So I'm going to find maybe the surface area or find the volume or find the mass of this solid. Well, in order to do that, I need to know what the thing looks like. Now, I don't have to graph things in general, but if I look at a formula or something with X's and Y's and Z's all over the place, I said, it's one of these. Now, if I wrote the equation of a sphere, I don't think that's an issue. I think that's a fairly easy one. But what if it gets a little bit more complicated? So I'm going to walk you through the process of how to make the conclusion. Now, most textbooks don't spend a lot of time telling you how to make the conclusion. What they do is they give you a whole bunch of equations, and then they tell you this is the shape. But you can't memorize. There's an infinite number of variations. So let's start simple. Let's suppose I have something of the form, let's say 3x squared plus 2y squared plus z, and that equals, actually, I'll say minus z, and that equals 10. Okay? And I'd like to know, what is this? Now, if I can graph it, that would be really nice, but more importantly, I need to know what it is and potentially where is it on the XYZ situation. Now, the first and foremost, we're primarily going to work with conic sections because conic sections are fairly simple for us to analyze. That's why at the end of Calculus 2, you reviewed your conics in 2 dimensions. So then you could talk about what conics in 3. So what we're going to do is look at what are called the cross sections of each of these. Now, the cross sections, I'm going to basically make them like cylindrical surfaces. Whatever this thing looks like in 3D, I'm going to fix one variable at a time and make that variable a constant. Then that tells me what all the cross sections parallel to a plane look like. You're not going to replace the variable with a particular constant. That would be incorrect. In fact, the worst thing you could ever do in any conceivable scenario is try to replace variables with the number 0, because you're going to find the majority of the time, then all of your other coordinates are going to be imaginary numbers. There is never a case where you would replace a variable with 0. That's something else. That's called a trace. And that has nothing to do with what we're doing. That's completely meaningless. Where a graph is cut off by the XY, XZ, or YZ planes isn't how you're going to determine the shape. So let's start in the XY plane. That means Z is going to be constant. So I will have 3x squared plus 2y squared minus k equals 10. So what is that? Well, if I rewrite this as 3x squared plus 2y squared equals k plus 10, k is a constant. This is an ellipse. In the xy plane, my cross section is an ellipse. Now, clearly, it's an ellipse. K has got to be greater than or equal to -10. Okay, because if k were less than -10, then I would have imaginary coordinates, and you can't have imaginary coordinates. Now let's look at the xz plane. In the xz plane, y is held constant. So now I have 3x squared plus 2k squared, and you can use k each time. All right, make sure you're muted, please. A lot of background noise there. Now, these guys are together, but that's a z. I might want to solve for z. It might be more recognizable. So perhaps I'll write this as z equals 3x squared plus 2k squared plus 10. That's a constant. Z equals x squared. That's a parabola. Now, it doesn't matter what the value of k is. And then finally, in the yz plane, okay, in this case, x would be held constant. So I have 3k squared plus 2y squared minus z equals 10. And once again, I'm going to solve for z because I can isolate the one variable. So z would equal 2y squared plus 3k squared plus 10. And once again, that looks like a parabola. All right. So in order to determine what the original shape is, I examine the three cross sections, what they look like in each plane. Not projected onto the plane, mind you, because there may not be a projection onto the plane. There usually isn't. So I have an ellipse and two hyperbolas. So how do I name the thing? Well, first and foremost, you're trying to acquire the title of oid, O-I-D. Oid, that's the crown. Oid literally means like. So this is mostly parabolas, so it's parabola-like, meaning this is a paraboloid. Okay, it's not a parabola. Parabola is two-dimensional. This is a paraboloid. But what type of paraboloid is it? It's an elliptical paraboloid. I'll write it out. Elliptical. It's an elliptical paraboloid. Now, if I were to actually try to draw a picture of this thing, let me leave myself some space here. I never need you to draw a picture, but sometimes a picture is very useful in trying to determine what the shape looks like. Okay. What this is going to be primarily, it's going to start 10 units below the axis and basically look like this. Okay. It's parabolic as I go all the way around. And if I'm standing on top of the z-axis and I'm looking straight down, I'm seeing an ellipse. Okay, so it looks kind of like this, kind of a squished bullet. Bad analogy, but that's what it looks like. So if I understand, oh, an elliptical paraboloid, that's what it would look like. Now, if the elliptical cross section turned out to be circular, then I would call it a circular paraboloid, and it would be, perfectly round. This one is a little bit longer in one direction than the other. So this is how I determined it. Now, drawing the graph isn't always necessary, but sometimes it's very, very useful. Now, remember I said before that the K had to be greater than or equal to -10 in that one cross section. Here's why, because that's where the vertex was 10 units down. It wouldn't have kept going. So let's try another one. Suppose we have something, let's say, we'll do an easy one. I've got, I'm going to not even bother with coefficients too much. Let's say I have 2x squared plus 4y squared minus z squared equals 8. Okay, and I would like to know, well, what is this then? Okay, so if we're trying to determine what this thing is, once again, we're going to look at the individual cross sections. We're not going to try to draw a picture, and we're certainly not going to sit there and plot points. But because you see the variables are being squared, so you tend to think, okay, conic sections, meaning circles, ellipses, parabolas, hyperbolas are what most of my cross sections are going to end up looking like. So in the xy plane, okay, that's where z is held constant. I'd have 2x squared plus 4y squared minus k squared equals 8. So I'll just write equals 8 plus k squared. Now, I have a sum of squares here. I don't have anything here. There's no sum of squares. A sum of squares is the only possible equation you're ever going to see that potentially has limitations. If I have a difference of squares, a difference of squares can be positive or negative. If I only have, if I have like x plus y squared or something like that, that can be positive or negative. There's no issues. But a sum of squares can never be negative. The right side is 8 plus k squared. That's always going to be positive, so there's no issues here. There's no values of k that I cannot use. Sometimes we're going to come up with issues. We'll call them restrictions. This isn't one of them. So clearly, this is an ellipse with no restrictions whatsoever. Now, the xz plane, I have 2x squared minus z squared, and I'll throw that on the other side just to make it easier to read. I have a difference of squares. This is a hyperbola. Now, a hyperbola never has any restrictions whatsoever because I can be positive or negative. And finally, the YZ plane, I'm going to have 4y squared minus z squared equals 8 minus 2k squared. And once again, difference of squares, this is a hyperbola. Right? There's absolutely nothing challenging algebraically in what I'm doing here and identifying the shape. So now, who wins here? Well, hyperbola wins. So this is a hyperboloid. And once again, it's elliptical. So this is an elliptical hyperboloid. And what this looks like, in this case here, because the elliptical, again, I made it the XY. Kind of look like this. It's not the greatest shape. I like to think of this as kind of like a big bale of hay, you know, huge bale of hay where I've got a rope in the middle and I squeeze the rope really, really, really tight. So it's narrower in the middle, okay? Or be like if I put on a really, really, really tight belt around my body, you know, make my body go like this, you know, squish in the middle. So this is called an elliptical hyperboloid of one sheet. An elliptical hyperboloid of one sheet, because it turns out there's more than one type of elliptical hyperboloid. So this is one I do not memorize, okay? You notice all of the variables in this case were squared, but I have signs that are changing. Because I have opposite signs, that's where the hyperbolas are coming from in the cross sections. If all three of these were plus, then all of my cross sections would have been elliptical, and this would have basically been an egg. It wouldn't be a sphere because my coefficients are different. It'd be more like an egg, okay? And we'd call that basically an ellipsoid. You wouldn't say elliptical ellipsoid, that's redundant. That would be like calling a sphere a circular spheroid or circular circuloid. No, it's a sphere. You don't have to get clever with the naming. Now, I want to do something really, really similar to this one, but this time I'm going to change one of the signs. Actually, no, I'm going to change the whole thing. I'm going to do it. Never mind. I'm going to do a whole different one. Too confusing if I only change one thing. All right, so let me take it really, really simple one here. How about x squared minus y squared minus z squared equals 4. I'm not even going to throw coefficients in this time. I'm just going to make it a little bit easier. Coefficients don't really mess things up, but sometimes we're looking at the wrong thing. All right, now this looks very similar to the one we just did. I have squares and I have signs that are different. Okay, they're not all the same sign. If all three of these were negative, then this would be impossible. We would only have imaginary numbers, and you cannot have a shape with any imaginary coordinates. That's not possible. Interestingly enough, on quiz 1, when you were finding the first problem, I gave you a sphere and I asked you for the center and the radius. I actually got imaginary radii, which makes no sense. That's impossible. That means there was no shape, not even one point. Now, you can't have imaginary coordinates in the real system. So, do it again, xy, xz, yz. This should be relatively simple. So xy, I have x squared minus y squared. Throw that over, equals 4 plus k squared. In fact, let's just do all of them real quickly. xz, so I have x squared minus z squared equals 4 plus k squared. And finally, yz, yz, I'd have negative y squared minus z squared equals 4 minus k squared. Great. So let's identify what each of these are. Both of these clearly are hyperbolas because they're differences of squares. Now, this one is a bit of an issue. I know what to do with sums of squares. I know what to do with difference of squares, but these are both negative. There isn't any shape where I have negative square minus square equals something, because if the right side's positive, again, I only have imaginary numbers. Yikes. So what we're going to do is rewrite this equation. Let's multiply both sides by -1. Then I would have y squared plus z squared equals k squared minus 4. Oh, that's so much better. Now I have a sum of squares. This is not a circle. This is not even possible. That looks like it's a circle. It's a sum of squares. But look at this quantity here. Can k be any real number? K squared minus 4 must be non-negative. Let me write that down. K squared minus 4 absolutely has to be greater than or equal to 0, which would mean that k squared must be greater than or equal to 4, which would mean the absolute value of k must be greater than or equal to 2. That is a restriction. It's a fairly serious restriction. So I'm going to write it like this. If the absolute value of k has to be greater than or equal to 0, then there's a gap there between -2 and 2 for the k that there won't be anything. Now, what did k represent in this? K represented the x value. So that means along the x-axis, there must be a gap. Ooh, that's kind of cool. I wonder what that looks like. So what is my shape, first of all? My shape is a circular hyperboloid. I'm going to hold off on the second piece because we're not done. Now you have all of your information right in front of you. So if I were to draw this one, again, that's the z, that's the y, and this is x coming out at me. Turns out I'm going to go 2 units out in the x direction. And then I'm going to go back 2 units in this direction. It's still a circular hyperboloid, but with my bale of hay example that I did, remember I tightened it really tight. I tightened it so tight, it snapped into 2 pieces. And these 2 pieces, this was my original bale of hay, but I snapped it into 2 pieces. This is +2 units out. This is -2 units out. And then it goes forever and ever. So this is a circular hyperboloid of 2 sheets. Why 2 sheets? Because there's 2 separate pieces. Now, going back to the first example and this example, how would I know the difference? Because in the previous example, there were no restrictions on my sum of squares. But in this example, there was. K had to be big enough in absolute value so that I didn't have a sum of squares equaling a negative quantity. Now, of all of the shapes we look at, sums of squares are the only ones you got to be particularly careful with. A sum of squares cannot be negative because that would mean you have imaginary coordinates. Okay, so I want to make sure everybody's got that one. Now, one of the things that I noticed, and some textbooks are guilty of this, there will be textbooks that when you're doing what I'm showing you to do the cross sections, they'll have you just, oh, plug in a 0. First of all, you can never do that. And 99.997% of the time, I think it's 997% of the time, you can't actually tell what the shape is, even if you did have a situation where you could do that. You see, if I replaced x with 0, then I have this, which is impossible because this is the equivalent of this. There is no graph. It's not possible to have x be 0. We just saw x had nothing between -2 and 2. You cannot replace a variable with 0. And having said that, about half of all the quizzes come in. That's what people are going to do on every problem because they are going to do it the way they think it should be done. No, that can't work ever. Pretty much ever. Now, I'll give you a really simple example of something that's not even complicated. Let's consider a sphere. Okay. I'm a one-trick pony. I can't draw line segments, but I can do circles and spheres. Okay, there's our sphere. And let's say this is the sphere x minus x naught squared plus y minus y naught squared plus z minus z naught squared equals, and I like to use rho. I'm going to draw it big. three-dimensional radius, we usually like to use a rho. Okay, so what's the big deal? Well, let's suppose that the center of my sphere is in the first octave. Okay, so my sphere is out here in the first octave. The entire sphere is located in the first octave. It never touches any of the planes. Another way of thinking about it, think of x naught, y naught, and z naught as being fairly large numbers, and think of the radius as being small. Maybe I make the center 10, 10, 10, but the radius is only 5. Then I never get close to any of the planes. If I tried to replace any of the variables x, y, or z with 0, then all coordinates would be imaginary because it never touches any of the planes. Therefore, none of the coordinates can ever be 0. The vast majority of all shapes that exist never touch any of the coordinate planes. So replacing a variable with 0 would only produce imaginary coordinates, and you can't figure out what it looks like if you did that. So we don't replace things with 0. What we do is we replace things with constants and see where it goes from there. So there's a simple example. So we've seen a couple of different types of graphs so far. Now, there is one truly evil graph. And as we know, when it comes to movies, the evil characters are always far more interesting than the good guys. Good guys are stale and plain and boring. But, everybody, at least in my generation, everybody wanted to be Darth Vader. Nobody wanted to be Luke Skywalker. That was just boring. Maybe nowadays. But so is there an evil version of this? Oh, yes, there is. There is one truly evil shape. Okay. And so let's look at the evil shape. I think the first one I did, what did I do? I did a elliptical paraboloid. So I'm going to draw something that's really similar. What if I did something like this? 2x squared plus y minus 4z squared equals 6. Okay. Well, I just did one that looked very much like this. So let's do xz or xy, xz, yz. You see, I can't look at that and tell you what it is. I got to look at the cross sections, and it's real easy. And there's no algebra to perform. I'm not solving anything. So this is going to be 2x squared plus y minus 4k squared equals 6. But because the y is, I can isolate the y, it'll look like a parabola. So I'm going to write y equals. So I'm going to write y equals negative 2x squared, throw everything on the other side, plus 6 plus 4k squared. It's a little more obvious now. This is y equals negative 2x squared plus a big constant. So clearly that's a parabola. Okay, now let's do the same thing. XZ, didn't give myself enough room here. So in the XZ plane, now I have 2x squared minus 4z squared equals 6 minus k. Now, because this is a difference of squares, it doesn't matter whether k is positive or negative. It doesn't matter whether this quantity is positive or negative, or even 0. So that clearly is a hyperbola. Hold on a second. I think I swallowed a bug. I do that every now and then. Okay, continuing. Now let's look at the YZ plane. So I've got y minus 4z squared equals 6 minus 2k squared. So like before, I'm going to solve for y. I think it makes it easier. Aha, clearly that's a parabola. All right. So parabola wins. This is a paraboloid. This is a hyperbolic paraboloid. A hyperbolic paraboloid is the only truly evil shape that exists. I mean, shapes can be evil. Oh yes, shapes can be evil. Yeah. How can a shape be evil? Because this shape confounds us. This shape causes nothing but heartbreak and difficulty from a calculus standpoint. So let me draw you a picture. And I'm going to give you sort of a generic picture, not necessarily this specific one, but a generic hyperbolic paraboloid. Kind of remember, it goes forever in both directions. Now, if I put this on top of a horse and then I sat upon it, I think all of you would recognize. We often refer to this as a saddle. And saddles are very interesting geometrically. Now remember, it's infinite. So this goes forever, right? This goes forever. It's coming out at you forever. Now, so why is this so evil? Well, we're going to see this. Hang on a moment. Let me hang on. Okay. People always wait. Robocalls, they love to do it right in the middle of class. Let's suppose that I look a bunch of the cross sections. These are all parabolic, right? They're all pointing down like that. I don't know if I just made it more confusing or less confusing. So now what I'm doing is I'm looking sideways. So this is what I see. So towards you, I see a series of parabolas. So I see parabola, 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 parabola as I'm looking. So imagine, in other words, I'm standing in front of the horse or behind the horse, looking at the saddle, and I see parabolas. Okay. So the vertex of the parabola clearly is the highest point on the parabola. So there's the vertex of the parabola. The vertex of the parabola is clearly the highest point on the parabola because they're all pointing downwards. Now, I'm looking at this hyperbola coming at me. And clearly, when I'm looking at that, that's the low point. So this is what I mean by confounding. Depending on my point of view, that point is either the highest or the lowest at the same time. Now, it can't be both. You can't be a maximum and a minimum simultaneously. That's impossible. But depending on my point of view, so if I'm looking at the horse straight on, this is clearly the highest point of the parabola. But if I'm looking at the horse sideways, this is clearly the lowest point of the dip. So we have a really clever name mathematically for this point. You'd never figure it out in a million years. It's called a saddle point, because that was the best we could come up with. And we study these a little bit later on when we start talking about maxes and mins and things like that of three-dimensional creatures. Saddle points are the most confusing and trickiest ones to deal with because, again, depending on your point of view, it appears it could be a max or a min at the same time, which means it's neither, of course. It can't be both, so it's neither. So we're going to come back to that one in a few weeks. So now that ends our topic on surfaces. I do not want anybody to memorize. Not, oh, that's ridiculous. Don't memorize. Just if you're given an equation, quickly come up with the cross sections and name the shape. But if I start talking about things like, elliptical paraboloids, hyperbolic paraboloids, very different. Okay. One sheet versus two sheets, things like that. Know what they look like because you went through a few of them. And every calculus book has lots and lots and lots of very good illustrations of what the pictures actually look like. So if you're saying, I'm not sure what that whole, hyperboloid of two sheets looks like. Oh, there's a picture in the book of what it looks like, a rendering. All right, now we're going to move on. The completely different topic now. So here's the concept I want you to think about. All right. We just did surfaces, and we can actually draw three-dimensional surfaces. Heck, anybody can try to draw a sphere or a cube or some simple geometric shape. But what if, okay, on the tip of my finger, I'm going to put a little sensor, and I always do this in the classroom. I'm going to fill up the room with particles that will be excited when my electronically charged finger goes through the room. So what I'm going to do, think of it like pixie dust. I'm going to go through the room with my little thing at the end of my finger, and it's going to create a clear and obvious trail. So you're looking, you see the trail like, Tinkerbell is flying through the room, and you see this curve in 3 dimensions. Now, that's physically impossible to give you a drawing on the board of a curve in 3 dimensions. It's hard enough drawing a line in 3 dimensions. So I'm going through space and coming up with this curve. Maybe that's my flight. I'm a bird. I'm in flight. There's no surface there. Okay, it's a curve. So how do I describe it mathematically? Ooh, that's kind of tricky. There's no equation I can give you. I can give you equations that describe surfaces, but there's no equation to describe a curve. So here's what we're going to do. As I move through space, I'm going to come up with a clever idea here. As I move through space, and again, you can't tell as I'm moving through space, but I'm moving through space in 3 dimensions. At time 0, perhaps I am right here. And then at time, however you're doing it, maybe every 1 second, every 2 seconds, I don't know. And then I am, let's say, here at time 2, and then I am here, and then I am here. For every unit of time that I'm measuring, I'm in a different place on this curve. I think that's fairly safe to say. So as I'm moving around, 1 second I'm here, 2 seconds I'm here, 3 seconds I'm here, and so on. But what I want to do is at every point on the curve in space, I want to think of a vector going out to that point on the curve, and the point on the curve is the terminal point of the vector. Okay. Now, the easiest way to describe this, first of all, let me give you an analogy. Maybe you guys have done this when you were kids. You've got that board and it's got all the nails on the board, then the nails move and you hold it up to your face. The nails are loose. And then you pull away and you have this beautiful imprint of your face. I don't know if you've ever seen that. It's kind of cool. Well, think of it this way. Instead, as I'm moving around the room, I've got all of these nails coming out of the corner of the room and touching my curve. So when I'm looking at it, I see this wave, almost like a seashell, but of nails coming out. Each one of these nails would be like a vector. So I have a bunch of things and it's creating this really cool wave, but all I care about is the terminal points of the vector. I'm giving you the definition of what is called a vector valued function. We are going to change the way we think of 3D motion in general. A vector valued function is a vector of functions where at every time I have a different vector. And the terminal point of that vector is the position on the curve that I want to be in. Okay, so it's actually a fairly simple concept. You're not going to draw 3D curves. That's too hard. But this is what we use. So if I want to describe motion in either 2 or 3 dimensions, I'm moving around. I want to talk about velocity and acceleration and things like that. I have to have something that I can work with, and that's what the vector valued function is. It gives me my position at any time. And so the notation we use for the vector valued function first of all, we write it as r of t. R is a vector. Why r? I don't know. That's just the universal choice. And r of t is the vector of x of t, y of t, z of t. X, y, and z are functions of t. T is the only independent variable. X, y, and z are not independent. There's only one independent variable in the problem. Again, that's t. So for every value of time that you put in here, it gives you a different x, y, and a z, therefore a different terminal point of the vector, therefore a different position in space. Now, we only do this in 3D. We can do this in 2D, by the way. And then every 2-dimensional curve, we'd find we get the same equation as if I'm going to do a circle, I can do it as a vector valued function because there's advantages of changing things to that. So first and foremost, this is what it is. Now we want to know about the calculus we can do. What about things like limits or derivatives or even integrals? Can I take an integral or a derivative of a vector? No, you can only take the derivative of a function. So what we need to do is define a way that I can link this up with derivatives and things. So we're going to start with the limit. We're going to define what it means to take the limit. So I want to take the limit as t goes to, let's say, some value. So say t goes to t naught of r of t. What we're going to say is that's going to be the vector This is the definition. We have 3 bars. That's the definition of the limit of a vector. You can't technically take the limit of a vector, so we're going to define the limit of a vector as being the vector of the individual limits. You see, I can only take limits of functions. X, Y, and Z are functions, and I'm taking limits of each of them. So when I make this statement here, this is how we are going to interpret it forevermore. Okay? And that's really, really important that we look at it that way. Okay? A vector of functions. Well, with that, we might be able to somehow define derivative. So let's see how that would work if I want to define a derivative. So let me erase. I'll leave the R of t up there. Now, let me remind you, if you came to my Calc 1 lecture today we did the definition of the derivative in Calc 1. In Calc 1, if y equals f of x, then dy dx, which equals f prime of x, is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. Hopefully you remember doing that in Calc 1 because that's how you derived most of your derivative formulas. This is called the definition of the derivative. Now what I'd like to know is, can I apply it to this thing? Well, I can't take the limit of the vector, but I know I can take the vector of the limits. So it's the whole, how do I do all that stuff? So let's start with this. I want to remind you of this. We already know that's true. So how can I make it work for here? So consider the following. Consider that I have r of t plus delta t minus r of t. Well, that kind of looks like the numerator, doesn't it? The problem is, if I do this, don't do this, I've invalidated. There is absolutely no such operation defined as division. If you have a vector and you have division, it doesn't really matter what you say after. You're making it up as you go. Remember, if a vector can be on top, then a vector can be on bottom, and that's an absolute mathematical statement. Of course, you can't, so therefore, that's garbage. So how do I get around it? Well, I don't divide by that. I multiply by that. Oh, that's how I get around it. I simply multiply that. So what I want to do is, if I do this in terms of the vector, what would this be? This would be 1 over delta t times the vector x of t plus delta t, comma, y of t plus delta t, comma, z of t plus delta t, minus the vector x of t, y of t, z of t. There, okay, I got it. So clearly this is true, but I can multiply this on the inside. And now I've got big humongous vector here, x of t plus delta t minus x of t over delta t. That I can do because that's a function. Y of t plus delta t minus y of t over delta t. And finally, z of t plus delta t minus z of t all over delta t. Now, I haven't done any calculus yet. I just expressed this statement right here. So now finally, we're going to define. I'm going to define the derivative of a vector. You say, well, why can't I take derivatives of vectors already? You can take derivatives of functions. A vector's a thing. That'd be like saying, I'm going to take the derivative of my television set. That doesn't make any sense. Your television set is not a function. A vector is a physical object, in other words. But a vector can be a vector of functions, each of which I can take the derivative of. So we are going to define d dt of r of t. We're going to write it 2 ways. Of course, we can write it as dr dt, still a vector, or just r prime of t. Both of these notations are totally acceptable. That's what we use. So what are we going to define that as? Well, clearly, this is the vector that I want to take the limit of. So what we're going to do, based on what we just said a moment ago, in terms of what a limit is, we're going to define this to be the limit as delta t approaches 0 of 1 over delta t r of t plus delta t minus r of t, okay? It's the limit of this, which would basically be the limit of this, but now I know I can move the limit in front of all three. That's what we defined earlier. And if I take the limit of this, isn't that the definition of dx dt? And the limit of this and the limit of this? So the beautiful thing, after all is said and done, when I move the limit on the inside, that is the definition of the derivative of x of t, meaning I have dx dt. Same thing here, dy dt, dz dt. And this is very comforting, by the way. Based on our definition of the limit of a vector being the vector of limits, then I can now, by using the standard derivative notation, I can say the derivative of a vector ultimately ends up being the vector of derivatives. And again, that's comforting because these are things that will be easy for us to do in general. So again, limit of a vector is a vector of limits, and the derivative of a vector is the vector of derivatives, because you physically can't differentiate. Think of that as being a shell you can't penetrate. So this is what we do. So we are going to use this information to make basically all of our conclusions over the next several weeks. So with that, I want to go on and show you something else. We're going to get in our Wayback Machine for a moment. At the very end of Calc 1, in my Calc 1 class, it's basically the last lecture. The last lecture in Calc 1, I do arc length and surface area. And then very late in Calc 2, we do arc length again, but from a parameterized point of view. I want to do arc length again, but now I want to do it in 3D. So I'm going to remind you what the Calc 1 was so that we can now easily extend it. Okay, the Calc 1 and the Calc 2 and then the Calc 3. So I have a point here called, x naught, y naught, and this point here is x1, y1, and I want to find the length of this curve. Well, the simplest way to think about that, again, I'm going back to Calc 1 for a moment, is think of splitting this up into a bunch of really short line segments, finding each of their individual lengths, because the length of a line segment is just using the distance formula from remedial algebra. I mean, that's a trivial thing. Square root of the sum of the squares of, delta x squared plus delta y squared. So how do I get the arc length? Well, then I'm going to eventually take a limit there. Okay, so that's what we did in Calc 1. So again, to remind you, in Calc 1, so I have, let's say, I'm going to blow up one piece. This is what I'm calculating. That's one of my little line segments, but that's the actual curve. So we usually use S for arc length. So this would be delta S, this would be delta X, this would be delta Y. And sort of like, again, going back to Calc 1, when we use differentials, I had the tangent line leaving the curve, and I was estimating the value on the curve by using the tangent line. We called those differentials. And we used a ds for that. And then we remembered that the change on the curve for delta X is the same as the change on the triangle. So delta X and dx were the same in this case. Delta Y and dy were the same in this case. We'll get to those notations later. I just want to do this. So what we're going to say here is that delta S can be estimated by ds, right? It can be estimated. They will be asymptotic. That's what the squiggles mean. Now, what is the value of ds? Well, distance formula. It's delta x squared plus delta y squared under the square root. I know that. That's not in doubt. So then the question is, what do I do from here? Well, from here, we do a little bit of simple factoring. My blue pen is starting to die on me here. So mathematically speaking, if I wanted to factor out in general, let's say I had something like this. I have a squared plus b squared, and I want you to factor out a squared. Well, how do I factor out an a squared? Easy. You'd write it as a squared times 1 plus b squared over a squared. Like, oh, okay, I forgot about that. Yeah, okay. I would like to factor out the delta x quantity squared from inside that root. Well, if I did that, then I would have 1 plus delta y squared over delta x squared all times delta x squared all under the root. Okay, delta x isn't 0. In fact, delta y could be 0, but delta x can't be. I'm moving left to right here. So I've got that, but then what's this? This would be 1 plus delta y over delta x quantity squared, all under the root, all times delta x. Oh, okay. Make sure you can see this easier. So if I said, I'm going to add up all of these pieces. Now, the first one, we technically would have delta x1 and delta y1. Then the second one, delta x2 and delta y2, and so on. Okay. So what we did was we said, well, then my overall arc length, which is s, can be estimated by the sum from I equal 1 to n of all of these guys added up. 1 plus delta yi over delta xi quantity squared under the root delta xi, where x was ranging from x0 to x1. Great. Okay. How did we get an integral eventually? Well, the Riemann sum means I'm going to take a limit. So s was equal to the limit. Now I'll remind you what the notation means in a moment, of the same quantity. Again, this is Calc 1. This is the last day of a semester in Calc 1. This says the norm of the partition approaches 0. The norm of the partition is the largest such, in this case, the largest such delta x. The largest such delta x is approaching 0. That's what this means. Because the split up was random. My delta x's are not all the same. So the norm of the partition, and the way I explained it in my Calc 1 class, some of you may have been in my Calc 1 class, is that I'm going to show up with a new weapon of choice. You see, I'm trying to become an evil genius, and all evil geniuses must have two things. Of course, your evil lair and your evil weapon. And my evil weapon is going to be a shrink ray. So what I'm going to do is show up to class, look for the biggest person in class, I'm going to shrink them down to 1 point. Now, the moment I shrink the biggest person down to 1 point, there is a new biggest person in class. Okay, now I shrink them down to 1 point. And I keep going. So eventually, even the smallest person in class is going to be the biggest person left. I shrink them down to 1 point. This is exactly mathematically what this situation means. If the largest delta x is approaching 0, then the next largest delta x is taken over. Now it's approaching 0. So therefore, all the delta x's will approach 0 at some point. That then gives rise, that's the definition of the definite integral of something. But here's the problem. Definition of what? Oh, so here's where the limit part's really cool. Now, I'm not going to rewrite it 10 times. We know that the limit of a quantity, limits are amazing. Limits of sum is the sum of the limit, right? The limit of a root is the root of the limit. The limit of the sine is the sine of the limit. Limits can move inside. The limit of a composition of functions is a composition of a limit is probably the most important. So the limit of this root is the root of the limit. I can move it inside. Now I have the limit of a sum. It's the sum of the limits. Now I have the limit of a square, which is the square of the limit. The limit moves all the way to the inside, which means, remember, the norm of the partition means the largest such delta x. Well, when I move it inside, I'm only looking at that delta x. So this statement would become the limit as delta x goes to 0 of delta y over delta x. Isn't that the definition of the derivative? Isn't this exactly? See, when we use function notation, we call it f of x plus delta x minus f of x over delta x. This is the exact same thing. This limit, by definition, is dy dx. That's why in the formula you learned in Calc 1, this was 1 plus the square of dy dx dx. All of you learned that. Very few people have ever seen the derivation because nobody does this except me. I'm the only one, crazy enough to even do this. The textbooks don't even do this. Every textbook I've ever seen, they don't even do this. They just say this. Well, where did it come from? Well, it came from this. Now, this is what we use. But in Calc 2, we do something different. We do a parameterized version really to set us up for Calc 3. You see, I want to find the length of a curve in 3D. Problem is there's 3 variables. So I can't do this exactly the same. So let me show you what we do in Calc 2. Then the Calc 3 will be just slam dunk, automatic, piece of cake. I mean, not even challenging. So I go back to this statement here, and this time I want you to factor out something else. If I wrote a squared plus b squared, I want you to factor out a c squared. But there's no c squared in there. Okay, I want you to factor it out anyway. Well, then wouldn't that leave me something that looks like this? Assuming c is not 0? Okay, I can always do things like that. I would like you to factor out the square of delta t. So if I factor out the square of delta t, then I would have this. And I know that's legal as long as delta t is not 0. Delta t is not going to be 0. Again, it's moving. It's the thing that's changing. But this is then delta x over delta t quantity squared plus delta y over delta t quantity squared. And then I'll pull that on the outside. So in Calc 2, what you did was you did this version, which is exactly the same thing, but now I'm parameterizing, I'm making both x and y functions of t. So let's fast forward to the end. Then it means my arc length was, let's say, from t0 to t1 of dx dt quantity squared plus dy dt quantity squared under the square root dt. This is the formula you learned in Calc 2, which is the same as what I just did, but now I've parameterized because I factored this a little bit differently. And as a result, you could do a few more problems than you could have done in Calc 1 because of the parameterization. So how does that help us in this class? Well, I'm going to move through 3 space, but I'm not going to go from x1 or x0, y0 to x1, y1. I'm going from x0, y0, z0 to x1, y1, z1. And I'm going to have the 3-dimensional Pythagorean theorem. And when I have the 3-dimensional Pythagorean theorem, we already know what that is. That's from the first day of class. So the only difference is now, think of this as being in 3 space. So I'm going to change this slightly. I am in 3 space here. Great. So now when I'm doing my little line segments, I'm going across 3 dimensions. Well, I showed you on the first day and the notes in the video and everything, the 3-dimensional Pythagorean theorem is 3 squares added up. Square root gives me the distance. So this is almost the same thing. Almost the same, only different. So the 3-dimensional ds involves the sum of delta x squared plus the sum of delta y squared, just like before, plus the sum of delta z squared. That's, again, coming from the 3-dimensional. Hold on just 1 second, please. Hold on. Somebody's banging at my door. Let me pause this for a moment. Somebody was banging on my front door, and it's a service technician, and he was going to continue to bang for a few minutes, and well, I didn't want that. All right, so this is the only difference now that we're in 3D. So when I fast forward, everything else is exactly the same, except that what am I going to have? I'm going to have one more term. That's the only difference. Okay, that's the only difference. In 3D, it's the same formula as it was in 2D because I'm using the 3-dimensional Pythagorean theorem. So we can easily find the length of a curve in 3D, assuming that I can actually integrate this. Now, I can ask the question and you can set up the answer. You may or may not be able to integrate the answer, but you can always set it up and fairly simply. So we'll do a couple of examples of that. But it turns out this is a very, very powerful tool. Okay, so I'm going to start with a simple one. This is my favorite one to start with. All right, I'm going to start with r of t equals cos t, sine t, t. And what does this actually look like, this particular crazy thing here? What does this look like? Well, if I were to, I want to actually draw a sketch of this, because you're going to run across this one often, or things of this nature. This is the vector valued function, so we can actually figure it out really, really quickly, believe it or not. So, for example, when t is 0, that would be radians, of course. I would be cos 0, which is 1, 0, 0. So I'd be here. When t is pi over 2, I'd be 0, 1, pi over 2. So right now I'm on the xy plane, so now I'm going to be up pi over 2 in 1 unit, so about here. Now when t is pi, I'll be at -1, which is back here, 0, pi. And as I keep going, what's going to happen is, I'm just going to tell you that's what it is. And if I go down, I can go like this. This is like one of the coolest things. It's this corkscrew. Okay, it is a perfect corkscrew, and it is called helix. Okay, for those in biology, that you know, a DNA strand. It's a helix. It's a spiral, and I don't need you to be able to draw it, but I need you to be able to understand that that's what this is. It's very cool. So suppose I wanted to find the length of a section of the helix. I've got a slinky and I want to cut it in pieces and find the length. It's really not that complicated. So I want to find the length of this. That's my x of t, that's my y of t, that's my z of t. So let's say, let's find the length, where t is between, just keep it simple, 0 and 2 pi. So I'm doing one complete loop as I'm spiraling upwards. So dx dt would be negative sine t. dy dt would be cos t. dz dt would be 1. Okay, next I want the squares of these added up. So it'd be cos squared t plus sine squared t plus 1 squared. Well, that's not too hard to figure out. That's just 2. So the thing that's going to go under my root is the number 2. I like that. So the arc length for this problem is the integral from 0 to 2 pi, because we set that up, of the square root of 2 dt. Now, as you know, when you integrate a constant, all you have to do is take the constant times the difference of the limits. So this would be 2 root 2 pi. Cool. That's it. That's all I had to do to find the length of this curve. So I do my scratch work first, and I add them up, make sure I take my derivatives correctly, and then pray that I get something I can actually integrate. Okay. So let me do something semi-complicated just to get the setup going. I don't need you to know what the curve looks like. But if you do know what the curve looks like, it's particularly useful. This is one of my favorite ones to discuss because I've actually been on this ride before. If you've ever been to the San Jose airport, I use that one because that's one I fly into typically. I go to conferences every year in Monterey, and I usually rent the car from the airport and then go. Well, the San Jose airport, the car rental is right across the street. It's like the 7th floor. And you rent your car, but when you leave, it's a helix that you go down. So you're starting up top and you're going down. And it's a helix that is extremely narrow. And when you're driving, you have to always look in the correct direction. If you look straight ahead, you can't actually do it. You actually have to look strong to one side because you're doing a strong turn. And it's the funniest thing when you see people stuck, which, by the way, every time I go, there's usually somebody stuck because they took it too wide or anything else. Because it's a helix shape, it's the exact same uniform all the way up and down rising, but there's certain things you have to do. We're going to discuss these things next day when we start talking about motion in general, velocity, acceleration. I like to use this example because it's very easy to illustrate and also easy to do the calculus on. But it's a very interesting phenomenon that they built a ramp to leave that was a helix, but a really small helix. So it's difficult to negotiate. If you've ever been on there, you know what I'm talking about.
Professor, before you erase that, I have a question.
Oh, yes.
Where you have dx dt squared plus dy dt squared plus dz dt squared, how'd you get cosine squared plus sine squared if dx dt?
Oh, I just wrote it. Yeah, thank you. It should be sine squared plus cos squared. Yeah.
Okay.
I'm just being lazy. You're right. I should have wrote sine squared plus cos squared, but same thing. I got it from that row up here. Exactly.
Okay.
Yes,
thank you.
I'm glad you asked. I don't want anybody to be confused on that. So let's do something just slightly more complicated. Let's suppose that our R of t is 3t squared square root t 5t. And let's keep it simple. T is going from 0 to 4. I would like to find the length of the curve that this vector value function generates. Now, the idea being, if I replace t with 0, clearly I'm at the origin. And now I'm going to start moving around space. I have no idea what this looks like, by the way. I'm going to be moving around space. So between t equals 0 and t equals 4, how long is that curve? It's not as simple as saying, well, let me find 0, let me find 4, let me find the length as that for that line segment. No. We're finding the length of a curve. We got to do this. Now, the problem is when I do this, I may or may not get something easy. I don't think we're going to be able to finish this one, but I don't care. I just want to be able to write it down. So dx dt, dy dt, dz dt. Let's go ahead and indicate each of these. dx dt, that's 6t. dy dt, that'd be 1 over 2 root t. dz dt, just 5. So next, dx dt squared plus dy dt squared plus dz dt squared is equal to, I'll write it up, 36t squared plus 1 over 4t plus 25. So I can say with certainty that the arc length is the integral from 0 to 4 of the square root of this quantity dt. Great. Now wave at it as you walk away because we won't be able to integrate this. If I just make up a random position vector, in all likelihood, I'm going to get an integral that I can't actually evaluate. We'd have to be clever, use other means, maybe power series, just something nasty. But I wanted to be able to express the integral. You see, this is real life. I actually need to know this answer. Well, at this point, I'd probably use computer technology. And that although it can't do the integration, it can give me a numerical approximation that is accurate to any number of decimal places. That's what we would use the computer for. But I would need to get it this far before I could even use the computer. Now, you might argue, well, if I put all this over a common denominator, if I do certain things, I might be able to manipulate it. And you're right. And often you will. And in fact, when you go through the homework in the textbook, it's reasonable to say that all the homework problems you will be able to integrate because they're reverse engineered to set up with friendlier values, let's say. But in general, the process for finding arc length is given this, I find these, I do the sum of the squares of these, I throw them in the integral, and hopefully I can integrate. Now, when I ask the questions on quizzes and exams, you will be able to integrate. And often it will be as simple as that helix was. Often I'm going to end up integrating a constant because we love using sines and cosines when we discuss motion because, you know, that gets me turning around. But when you have sines and cosines involved, the squares of their derivatives, when added together, more often than not produce constants, which is a nice thing. So I will stop now.